the converse of the previous theorem, the one that states that if a sequence converges to a given limit, all of its subsequences will also converge to the limit, is false. Can you think of a sequence which diverges, but which has convergent subsequences? It's a neat little exercise. If the converse was true, every divergent sequence would be such that all of its subsequence would also be divergent, but it's not what's actually happening. The next result, the centerpiece of this section, is both surprising and important, the Bolzano-Weierstrass Theorem. It's also a result that highlights how you use a lot of the intermediate results that we've found up to now, that we've proven up to now. So the proof is quite instructive from an analytical perspective. Statement, again, quite simple. Assume you have a bounded sequence, not necessarily convergent, not necessarily monotone, just a bounded sequence. Then it has a convergent subsequence. Let's see what the proof would look like. Well, the sequence xn is bounded, so there's some interval which we'll call I1 with endpoints A1, B1, such that the sequence, or at least all of its terms, lies in the interval. Right? Another way to say this here is that A1 is smaller than xn is smaller than B1 for all n. This is bounded. It's in the interval. You could also write it as the sequence is contained in the interval I1. Now, I've used a notation similar to that one in previous videos when I talked about subsequences. I1 is not a sequence. I1 is an actual set, an interval. And when I use the inclusion symbol here, I'm actually talking about inclusion of sets, not that this is a subsequence. So just be careful. I'll get confused by the similar notation. We are going to build the subsequence xnk, which is the convergent subsequence. So our goal here to build this subsequence, which will converge to some value x or x star. Our first index n1 will just be 1. In that case, xn1, which just x1 belongs to the first interval I1. And what we do know as well is that the length of I1, this distance here, is going to be b1 minus a. Okay, now let me rewrite that in a slightly more evocative form. Okay, that the length of I1 isn't just b1 minus a1, it is really b1 minus a1 divided by 2 to the power 0. Why we use this notation will become evident as we move on with the proof. I'm going to build now 2 subintervals of I1. So I had my original I1 here. Look at the center point, the midpoint of the 2. The first subinterval I'm going to call I1 prime. Nothing to do with derivatives, it's just a notation. The second subinterval I'm calling I1 prime prime. And now I'm going to build 2 sets of indices depending on where the terms of the sequence fall, depending on which subinterval they fall. First, let me explicitly write down what I1 prime would be. I1 prime prime. We define the following sets. Set A1 will be the set of all the indices n for which n is greater than n1. So we're looking at all of the terms after xn1 in the original sequence, for which xn I1 prime and b1 will be, you can probably guess what it will be. It's the set of all indices greater than n1, the first term of the subsequence, such that xn belongs to I1 prime prime. Now we know that the sequence xn is bounded by a1, b1, and in particular what it means is that all of the points of the sequence are in here. Now some of these points might repeat themselves as value, but in terms of terms in the sequence, there's going to be infinitely many of them in here, a countable infinity. What this means is that at least one of A1 or B1 must be infinite countable. Right? If that wasn't the case, if they both had finite cardinality, they both had a finite number of indices, well, you would have a sequence with a finite number of terms. Again, not necessarily a finite number of values, but a finite number of terms, and that's not a sequence. A sequence has infinitely many terms to start with, so they can't both be finite. At least one of them has to be infinite. It's conceivable, all right? It's conceivable that both of them would be infinite, right? So we do have that the union of A1 and B1 is basically all of the n's in n such that n is greater than n1, and that's an infinite set. That's a set with cardinality omega, a countable infinite. Well, what are the options? If it is A1, which is infinite, what you're going to do is create a new interval, I2, which will be I1 prime. So the interval that contained infinitely many points to start with of the original sequence. So now A1 being an infinite set of integers is not empty, and by the well-ordering principle, every set of positive integers which is not empty has a smallest number. I'm going to say the smallest number is n2. If A is finite, then you don't have a choice. It must be that B1 is infinite. In the first case, possibly both A1 or B1 were infinite, but you only cared about the first one if it was infinite. So if A1 is finite, then B1 is infinite. And then you would set I2 to be the second half of the interval. Again, B1 is not empty. The well-ordering principle implies the existence of an N2 such that N2 is smaller or equal to N. Well, I wrote for every N in N here. That's obviously not possible. What I'm really talking about is this N2 being minimal for the set A1. So it has to be for every N in A1. This one here would be for every N. No matter which one of these two options is the one that occurs in reality, there is an integer n2 which has to be greater than n1. Why is that the case? Well, a1 and b1 as sets were defined as a collection of integers which were all greater than n1, strictly speaking, and then that belongs to either one of the two subintervals. So we know here that the n2 that we get in both cases would be greater than n1. That's a thing. And the other thing is that the corresponding xn2 would belong to the interval I2. By construction, we've picked the smallest integer n2 in A1 or in B1. And if you were in the first case, you were looking at I1 prime, but the corresponding xn2 is going to fall in I1 prime. And if you were in the second case, you're looking at I1 prime prime, but the corresponding xn2 would fall in I1 prime prime. In both instances, xn2 would fall into the interval that we've chosen to call I2, depending on which one of those was occurring. So xn2 is an I2, but we can say a little bit more here. I2 as an interval is actually contained in I1. It's one of the two halves of I1. And perhaps more importantly, the length of I2 would be half of the length of I1. So B1 minus A1 divided by 2 to the 0. So half of that is actually going to be B1 minus A1 to the power 1. I don't know if you see where we're going with this, but we have built, or at least we've started building a sequence, which is going to be a subsequence of the original sequence xn. We have an xn1, and then a term that came after xn1, xn2. So we're building the subsequence, and it looks as though we're going to be building as well a sequence of intervals that are nested. I1 contains I2, and we're going to play the same game with I2. Find an interval I3, which will contain xn3, which will be one of the terms in the sequence, which will be the next term in our subsequence. And so we will have a subsequence where each term belongs to an interval which is nested inside a sequence of intervals. And all of the intervals have a length here which will shrink by 2 at every step. So the infimum of these lengths will go to 0, and then we'll be able to use the nested intervals theorem to show that the intersection of these intervals is not empty, and in fact it is a single point, and that single point will be the limit of the subsequence. But let's try to formalize that a little bit. What we've really done here is establish the base case, the base step of an induction process. So now we're going to assume for equals k, we have the following. We have an interval ik minus 1, which contains an interval ik. The lengths of ik minus 1 are going to be respectively b minus a divided by 2 to k minus 2, and b minus a divided by 2 to the k minus 1. We'll suppose further that there exists indices nk minus 1 and nk such that nk minus 1 is smaller than nk, and finally that xnk minus 1 belongs to the interval ik minus 1, and that xnk belongs to the interval ik. So that's the assumption for the induction step in mathematical induction. And what we're going to want to show is that we can find an interval ik plus 1, which will itself be contained in ik, and hence contained in ik minus 1, with length b minus a divided by 2 to the power k, an integer nk plus 1, which will be such that nk plus 1 is greater than nk, and for which x nk plus 1 is in the interval ik plus 1. And if we have that, then we will have shown by induction that we have a sequence which is a subsequence of the original sequence, and that each term x and k resides in an interval which is part of a nested sequence of intervals whose length going to 0 and k increases, and that intersection, the singleton, will be them. That's all we're doing. I made a little simplification for the writing to make this easier for me not to get lost. What originally I had called B1 and A1, I'm just calling B and A here. So B is B1, A is A1, just to try to minimize the number of indices that I'm carrying, but technically speaking, that is meant to be B1 and A1. So how would we prove then the existence of this interval ik plus 1? But we need to define it. We need to set it. You won't be surprised to hear that we're going to build the interval ik plus 1 in much the same way as we built the interval I2 from the initial interval I1. We'll write the interval ik as alpha beta. Set two new intervals. We define using the midpoint of alpha and beta. Ik prime is the interval alpha to alpha plus beta divided by 2. Ik prime prime is the interval alpha plus beta divided by 2 to beta. And this is your ik prime and this ik prime prime. Now we define sets ak and bk. They're going to be sets of integers, specific integers which are all greater than nk. We already have an nk by assumption in the induction step. So here we're looking for the indices greater than nk which belong to the interval ik prime. For the other one would be the indices greater than nk which belong to the interval ik prime prime. Now it's impossible for both of these sets to be finite, right? If both of these sets were finite, AK union BK would be finite, and we would just have a finite number of terms in the sequence in there, but that's not possible. It's not the way it's been defined. So they cannot both be finite. If ak is infinite, then we set ik plus 1 as ik prime, and before, ak will have a smallest member, which we know exists by the well-ordering principle. The smallest member, we'll call it nk plus 1. After this means that x nk plus 1 belongs to I k plus 1. If ak is finite, the other possibility, then we set ik plus 1 to be ik prime prime, and then the smallest member, again by the well-ordering principle of bk this time, would be nk plus 1. We'll be calling it, we're calling it nk plus 1 as again, or as before, xnk plus 1 belongs to interval I nk plus 1. Sorry, I wrote I nk plus 1, but it isn't the case here. Ik plus 1. But by construction, ik contains the set ik plus 1. By construction, nk plus 1 is greater than nk, because this is a member of the set ak or bk, which is just the integers past the point nk. So we got that. And the length ik plus 1 is going to be half the length of ik, which we knew to be b minus a divided by 2k minus 1 gives you b minus a divided by 2k. So what do we have here in mathematical induction? On the one hand, we've built a sequence of nested intervals. We know that the length of each interval is b minus a divided by 2 to the k minus 1. We know that we have a number of indices nk, for which the term xnk belongs to the interval ik, again for all k. And finally, the sequence of indices here is a strict increasing sequence. And so that in fact, these two things here are telling us that xnk is a subsequence of xn, and because the limit when k goes to infinity of the length of the kth interval will be the limit when k goes to infinity of b minus a divided by 2 to the k minus 1, which we know to be 0. Then all of the hypotheses of the nested interval theorem are satisfied, which means that the intersection of the IKs is going to be a single point that I'm going to call x star. But what you need to show here still, that the limit of the x and k that we found when k goes to infinity is in fact x star. And that's the candidate for the limit that we found for that specific subsequence. You had a lot of options along the way. You might have built a different subsequence. Like when we pick the A1 and the B1, we go through the step of saying, well, one of those is infinite. Let's assume that A1 is infinite. But there's nothing to force you to always say that A1 is infinite. You could alternate. You could do it with B1 as the main driver instead of A1. For now, we've picked the procedure where it's always the left hand of the left subinterval of the interval that we consider first, but it doesn't have to be done this way. At any rate, does this limit exist? Is it equal to x star? So how do we prove this? Well, we need to use the definition of the limit. Let epsilon be greater than 0, we are going to look for a k epsilon. Usually we call it n epsilon, but here k goes to infinity, so why not call it k epsilon? Looking for a k epsilon, an integer such that the distance between the candidate for the limit x star and the terms of the sequence x and k get arbitrarily small, and k is greater than k. This is what you're looking for. Well, which one are we going to pick? We're going to pick a specific k epsilon by the Archimedean property. You can find an integer that we'll call k epsilon such that k epsilon is greater than the logarithm in base 2 of b minus a divided by epsilon plus 1. Well, we know that's doable. This quantity here is a real number. Epsilon is not 0, so I can divide by epsilon without causing a problem. With the logarithm of a positive quantity, I'm happy. Plus 1, this is a real number. I can find an integer greater than that. If that's the case, then if k epsilon satisfies the inequality that we just saw, the expression 2 to the k epsilon minus 1 will be greater than b minus a divided by epsilon. And that will mean, amongst other things, that epsilon is greater than b minus a divided by 2 k epsilon minus 1. And that, of course, is greater than 0 by construction. Let's verify that the definition of the limit applies to the subsequence x and k with this choice of k epsilon. Well, for every epsilon greater than 0, there exists a k epsilon greater than log base 2 b minus a divided by epsilon plus 1, such that whenever k is greater than k epsilon, then 2 to the k epsilon minus 1 is going to be smaller than 2 to the k minus 1. But that doesn't depend on the actual definition of k epsilon here. As long as k is greater than k epsilon, this is going to be true. But since our value x star belongs to ik for every k, and because x and k also belongs to ik, we have that x and k minus x star is going to be an absolute value smaller than or equal to b minus a divided by 2 to the k minus 1. Why is that the case? Well, think back to where we are. Here's our interval ik. Here's potentially our value xn. Here's potentially our value xnk. And they are definitely within this distance of one another. Well, this distance is the length of the interval ik, and the length of the interval ik is b minus a divided by 2 to the k minus 1. Now we've picked our k epsilon to be such that, so whenever b minus a divided by 2 to the k minus 1 is smaller than b minus a divided by 2 to the k epsilon minus 1, this will actually be smaller than epsilon. That's how we picked the k epsilon right here. So we conclude from this, the limit when k goes to infinity of x and k is actually equal to x star. And we have found that the subsequence that we found, the x and k, is in fact a convergent subsequence and converges to x star. Every bounded sequence has at least one convergent subsequence. Bolzano-Weierstrass theorem. This theorem has everything. Think back to it. We're using the nested value theorem. We use the definition of the limit of a sequence. We're using mathematical induction. This is a perfect example of how all of the analytical pieces fit together. And I think this is a good place for you to stop and consider your understanding of this proof. Do you see how all the pieces fit together? Do you see how they were necessary to start with? Do you see where the hypotheses come into play? Like, there was just one hypothesis to this theorem, that your sequence was bounded. Where does that come into play? It comes into play at the very start when we say that all the values of xn lie within the interval a1, b1. But that's the only place that it came into. I really like this result. Big fan of it.